let's now talk about boosting, which is the final model of today's session. So kind of the basic idea in boosting is quite simple. So boosting is also a ensemble method similar to bagging in random forest, but importantly, boosting does not use the bootstrap. So for bagging in random forest, I always bootstrap the data and then fitted a model on each of the bootstraps. Importantly, this could also be done in parallel. Effectively, I can resample on many different cores and I could kind of fit those models and then gather all the data together. This is why random forest could be quite interesting, also because it could be done in parallel for very large data sets. Now boosting is a form of sequential model where I kind of update my data and a little bit at a time. So very different also conceptually to the previous one, where kind of each of the trees should be as big as possible, very low bias, and I bring down the variance using the bootstrap as I did in random forest, for example. Here, each tree should be very tiny. I want to have very tiny trees. Each one learns a little bit, but then I will effectively update the data to take away, in a sense, what the first model already learned, look at the remainder, and I train a new very simple model and take it away, and so on and so forth. So effectively, I have very simplistic models. Sometimes the trees in boosting are just what is called stems. They are sometimes just effectively trees of like 3 nodes or something like this. Very tiny. All are very small, but then each one learns a little bit, and by adding them all up, the majority will give something quite interesting. Actually, people in social science use this as a kind of motivation why, for example, maybe very simplistic actions amongst participants collectively can give some very interesting behavior. So it's a kind of mathematics. The mathematical model of boosting is a model which shows some property like this, that kind of very simplistic models individually in aggregate can get a very kind of collectively, they can make a very good prediction, even if every one of them doesn't maybe know that much the subjects there. And it's a nice mathematical model which shows that. Again, this is not the reason why we use it, it's just why this mathematical model might be appealing from a conception point of view to some. So this is very nice, but it's also still a bit vague. So what do I mean by kind of explaining a little bit of the data, and then we look at the remainder to fit a new one, and then we explain a little bit and we look at the remainder. The basic idea is a bit like if I had individual data points here and say I fitted a function here, then I could say, okay, now this function already say explains this basic behavior. As I have a quadratic function at most, and I can already explain the basic trend in the data. But now I would still have those residuals which are unexplained, basically. So imagine originally my data was kind of, here was my coordinate system, and this was my original data. Now I could say the new data could be something like just the residuals, effectively, where now I have to get the blue dot here, where this one was kind of up, then down, then up, up, and so on. So my data would now just be the residuals of the previous model. I've kind of already explained away the upward trend. Now I'm looking at the variation. Now I might maybe fit another model of similar type here, which maybe, I don't know, explains this bit here. And now I can kind of take away what is explained here, look at the remaining residuals, now the residuals to the to this new model here, and kind of continue as before. So this would be a very drastic step. I take the data, I fit the model, and then effectively I get new residuals there. So effectively the data I fit to, or I can always fit to with the residuals. Now the first step, so I would always fit the model to my residuals. So I would first start, so originally my residuals are just my original data. Now I fit a model F basically for the first time. Now my my new residuals would just be said to be the old residuals minus the fitted model, say, for the first time. And now we fit again and again. I will just keep on repeating this process. So this would be the initial step. And then in the iteration, when I will go, say, from I to I plus 1, I will just keep on replacing my residuals by the previous residuals minus the function there, which would be effectively, so this would be the previous residual. Now let's get like a good example here. So the previous residual was this one here, and now the function, the fitted value of the function is this one here. So the new residual is this one here. I'm not sure whether you can see that easily. Let me maybe draw it again. So the new residual would be this one here, which was the old residual, which was just the value of the function, minus the fitted value of the function here. So this is what it looks like. Now I have updated it, and so on and so on. Now I can kind of keep on updating this model. But importantly, what would be my final function would be just a combination of those functions. Each time I fit a function, I will basically say my final function here will just be effectively a kind of sum of the original function. So what I predict, so if I do this I times basically here, then my final prediction function f of x will just be the sum of f of I basically of x. So this is the description what I just said, where effectively I start off with the original data and then I always fit to the residuals. So at first basically I say my original data is the first residuals, and then I fit to the residuals, take away what I learned, get new residuals, fit a new model, take away what I learned, get new residuals, and so on. And then the final model will just be kind of the sum of all the original models. So this is effectively how boosting works, but the difference is that it would be very drastic to take away everything at once, because maybe my first model was not very good, and now I kind of took away a big chunk here of a model which wasn't very good. So a better way is to introduce something which is called a learning rate, where I put a small parameter here. So it's not this small parameter here. So effectively, rather than taking away everything at once, so all the information I've learned, all this bit here at once, to get the new residuals here, what I'm doing is effectively I'm taking away this newly learned function times some multiplier, say 0.1%. So I'm taking it away a little bit, and then I'm still repeating the process. So I'm not doing so big steps. I'm moving in the smaller learning rate, and then obviously the kind of sum here gets also multiplied by a smaller function. Rather than kind of summing up all these individual predictions, I will sum them up with a little multiplier here, sigma I. So this would be the basic procedure. I start off with the original data as being my residuals, then I fit a model, take away what I learned, but only with a small fraction, not with the full force basically, only times a small multiplier, take it away from the original residuals, and I get new residuals. And then I keep on doing this. And finally I get a final predictor, which is just a kind of weighted sum of those individual prediction models. And this is exactly what boosting does, kind of more intuitively explained. And if you go to the textbooks, the Introduction to Statistical Learning, you can write down the algorithm explained with those formulas here, those equations. It will explain you this algorithm exactly saying first step would be initialize, then keep on doing, updating residuals with a small learning rate, and at the end of the day you will get the final function as being the weighted sum of the functions of the individual fits there, where each f here is a regression tree. I just drawn some kind of sloping function there because it was easier to draw and talk about it. But those f's here, those are all individual trees. Those f would be, say, a single tree, and as I mentioned earlier, it should be a small tree. So I fit a small tree, which would be this function here. I just drawn it as a line, but imagine it would be something piecewise constant. Then I go take away a fraction of what I learned, fit a new one, take away what I learned and fit a new one. This is exactly the procedure of boosting, and kind of this is basically the algorithm in words, where effectively I fit a decision tree, which could be a regression or a classification tree, and each time I kind of fitted a new model, I will take it away with some shrinkage, and I subtract effectively what I've already learned from the data, and I keep on repeating this procedure. So this is kind of the idea behind the algorithm. Is not very precisely written out here, but I think I've explained the formulas underlying it. So if you have a look at the textbook, if you want to, you can hopefully see exactly how it works. It's exactly those steps here, but I didn't want it to kind of make you work through all the math of the formulas, but I just wanted you to kind of understand the intuition. It's all about having the original data, fitting a very simple regression tree or classification tree, taking away a fraction of what I learned, and then repeating. And you repeat and repeat, and then your final answer is just a weighted sum over the individual one. So it's again an ensemble method, ensembling because I'm summing over individual trees, similar like boosting. The final would be some form of mean, so I'm kind of summing over all, like for the mean I would do 1 over n, the sum over all the individual trees, but here I have like lambda instead of 1 over n, and all these trees would be, rather than being different fits of different bootstraps, I'm kind of fitting always to the residuals in a sequential form here. So this is exactly how boosting works, and this is all what I wanted to say about the kind of algorithm of boosting. You could spend several lectures talking about the math behind this. There's actually some quite nice relationships of how actually some of the algorithms for Lassus work and how they relate to boosting, and boosting is sometimes also called gradient boosting, and you can not only apply it to trees, but you can apply it to other techniques as well. You can fill chapters with the context of boosting, but for what we are concerned, what I just explained very intuitively should hopefully be enough. But it's important for you to know basically some of the properties of boosting, and also some of like the way you should be using it. From the discussion we already learned that for boosting I want to have many small trees, whereas for bagging and random forest I want to have many very large trees, and then I just keep on bootstrapping. And you can also see a little bit in the performance picture. This is an example from the hard data, which is a data set you will also be working with, and here I fitted a random forest, bagging and boosting here, and I can see the random forest here is in blue, boosting is in green, and bagging is the red one. And if you just have a simple classification tree, would be the dashed line. So classification trees, obviously those are like multiple trees here, so I keep on 1,000 trees, 2,000 up to 4,000 trees here, which could be either by bootstrapping it, the data set is 1,000 times or 4,000 times, or by say keep on running boosting for as many steps. Obviously for the classification tree I would only have one tree, and this one tree would have given me an accuracy of around whatever 26.5% or something like this. So this would be the accuracy if I just use a single tree. It would be very easy to interpret, as we already said, but performance would not be as good. Now if I look at bagging, for example, I could get down to something which is roughly just of the order of 20% here, and I can see that it performs better than the simple tree, just already bringing the error down from 25% to 20%, but then it performs quite well already for very few trees. You see, I have like here, after I fitted it for a couple of times, I already get a very good performance here. Very quickly does the error drop. I mean, you can't, it looks like it's close to zero. I think it's like 10 trees or something like this, 10 bootstraps, and I've already gotten a big gain here. But then keeping on repeating it up to 4,000 times, I do not really gain anything new. But it also doesn't get really much worse, which is what I said. You can keep on doing it for as long as you like. It doesn't really, you're not really likely overfitting then. I mean, there's obviously some randomness, but roughly speaking, this thing drops extremely quickly, but then more or less there's constant here. Now, the same is true, roughly speaking, for the random forest. The random forest, because you have more independent trees, you can squeeze out a little bit more, and it requires you also a little bit longer. So here you have to go up maybe say to 100 trees first, but then once I'm going up to the 100 trees, then I kind of, it's more or less remains constant then. But then for the boosting, I can see boosting is very slow because I have a small learning rate. I only fit very kind of simple models, tiny trees with a small learning rate. It goes down very slow, so it starts off very badly here. I kind of, my error is much higher even than the simplest one. Even here where I maybe have fitted whatever 200 steps in the boosting, I'm not even better than a single tree. But if I keep on going, it will get better and better and better, and eventually at 4,000 trees it's around the best model of all. This is why boosting is quite good, it's quite famous, but you see also some of the difficulties. So if you have a lot of compute, if you can do a lot of work, you can potentially get amazingly good results from boosting if you're down here in this area. But if you only looked and had the computational power to go all the way up to here, maybe random forest would have been the best technique. You would have gotten that performance. If you wanted an interpretable model, you maybe could have chosen just a simple tree. So it doesn't really, there's not one good model here. It depends on really what you can do and what you're after. If you're after interpretation, the tree would be the best. If you're after best performance, but you can only allow yourself to do a small number of iterations here, in the bootstrap, for example, or in boosting, then potentially the random forest would have given you the best result. Now, if you had much more power and you wanted to get the best possible result, no matter the resource requirements, then boosting would have been probably the best choice here. And now I'm just trying to unclutter a bit the image. But this is just one example where I took one data set, the hard data, which we'll also talk about in tutorial, and applied all the different models just to see you the kind of benefits and how they could perform in practice. And that was the last thing I wanted to say about boosting. And now we can kind of, this slide where we kind of just talked about all of them brings us naturally to the conclusion.